Okay, just got off work. This is the habit I need to get into right now. Straight off work, 5 o'clock. Let's go. Right here. Boom. Okay, stacking the heap. Why? Yeah, I opened up the wrong program. Opened up my, Unreal Engine. So the last thing we had yesterday was what? Oh, plugging in specific oh yeah. Using passing functions via function pointers as arguments to other functions to receive as parameters. Passing functions to functions. It's just that in those functions, we need to evaluate the function pointer as a condition to make sure that it's actually valid. For example, I will have a function called doThing. Doesn't do anything. And then I'll have another function called useDoThing. And what does useDoThing take? It takes a pointer to a void returning function with no arguments. So a pointer to a void returning function that takes no arguments. A pointer to a void returning function with no arguments. And give it an identifier and we'll call it thing. So this is the thing that it's going to use. But when we actually use it, let's say it prints. And doThing prints thing has been done. Or rather, no passive voice, did thing. Boom. Okay? And then useDoThing is going to call thing. And we could do this two different ways. We could say dereference thing and call it, or we could just call thing like this. Do it either way. This is an implicit indirection, a dereference. Dereferencing is just called indirection. That's where you get the value from a pointer. And so we could either explicitly dereference indirect thing and then call it, or just call it and it's implicit. This is fine. And then we'll just call useDoThing. And what am I going to pass it? I'm going to pass it doThing. And I'm going to call useDoThing. And so I'm calling useDoThing. Look at the call stack here. We're going to see, okay, we're going to use doThing. And doThing is expecting a pointer to a void returning function. A pointer to a void returning function. In this case, and then it will call it. So it sees the pointer to the void returning function and then calls that pointer, or calls the value of the void returning function. So in this case, it just calls the void returning function, which is doThing, and then it prints doThing. We're going to skip over so we don't go and look into standard character output, and then see that it printed, and then it's going to return back to useDoThing, return back from their domain, and return back from their obscurity. Okay, that's done. So we have passing functions as pointers, passing functions to functions, etc. Okay, stack in the heap. A lot of shit here. A lot of learning. Okay, stack in the heap. So far, I picture the stack in the heap as I don't need to draw shit. I don't use my words. I need to get better at speaking. So far, I picture you have some limited piece of memory. Let's say it's this space. This is the stack. Stack is this limited bit, and apparently it's only a megabyte. Maybe it's 1,000. I don't think it's a gigabyte. I think it's a megabyte. It's a very small amount of memory. So it's 1,000,000 bytes in this case. So 250,000 integers, right? Because times 4 to be 1,000,000. So a lot of little guys. Eventually we're going to run out. So if we went into a loop and we kept creating more and more, eventually we're going to run out. But, or at some point, if we have a program that creates something and then it calls into something, it calls another function to create another thing that creates another thing. Eventually, we're going to run out of things to create. So we need some dynamic memory. We need extra memory because we don't have enough here. So what we do is we have this, every bit of area outside of this rectangle, this huge amount of space here is the heap. And the heap is this extra bit of memory that we can use pointers in the stack to say, hey, open up a little piece of that memory and let's use that. So instead of creating another thing inside the stack, instead have a pointer to the thing we need to create, but it's actually located out here. So we have this big expensive standard string, 8 bytes, holy shit, out here, and then I have a little pointer to a standard string inside here. So we can reserve little pieces of that memory, and once we finish using it, we close it back off and free it. So we're back just to the stack. Okay. Oh, and apparently some of the code is reserved to the actual code of the program. Some of it is memory for using things. Some of it is used for functions. I think that's the first part. And I'm not super sure about the rest. Okay, so we have a code segment, text segment. The codes, okay, this is the memory that a program uses, called segment. Different spaces that the memory is split into. Code segment is where the compiled program sits in our memory of the operating system, of the computer, of the machine, seems like. Okay. Code segment is where the compiled program, so the translation units in binary sit in memory. That way other code can, I guess, look there and call it, something like that. Code segment is read-only. So once it's compiled, it can't be changed anymore. It just runs, it just does stuff. It's procedural, stuff happens. And I guess it's procedural such that it does what it does. Sure, maybe things execute in a different order, not always the exact same, so maybe we're diverging from the definition of procedural here. Code does what the code does. Maybe a different piece of code is called. The point is that all the code there, that's all that can execute. Maybe it includes code for writing new code inside it, like a game where you can code inside the game, but that extra code isn't written from the game. It's written inside the game. So it's limited by what the existing code allows you. Because all that will ever exists. When you compile a function template, that's it, buddy. No more are going to be made once the program is run. They've all been compiled, that's it. The BSS segment. So there's a section for the code, the instructions. There's a section for zero initialized global and static variables. So variables that makes sense. That's why we can create standard string views at compile time. Even though I'm not sure if they just turn into C-style strings that are optimized away just like an integer. They're actually stored somewhere separately, where they're known at compile time. So their values are set to be 0, and then when the program starts, it picks it from these spots. Now I'm picturing the rectangle that's divvied up a little. Here are the instructions, and over here in this little corner are the 0 value initialized variables. And so once the program starts, boom, these guys are all zeroed out, and then the rest of the shit happens. Excuse me. The data segment, excuse me again. Excuse me, I've been drinking a lot of lemonade starting yesterday or day before. Excuse me. Day before yesterday, maybe? I don't remember. I think day before. And my gas has been scary. Felt like another gas. Alright, the data segment where, well, hold. 0 initialized, but then there's the data segment where the non-zero initialized global and static variables are stored. So it looks like program starts, it has instructions, and the compiler will read off the instructions, or whatever it is that's executing the instructions, read off the instructions, do its thing. But not yet. I guess before it starts reading off the grocery list, it does the necessity. We need milk, we need eggs, we need apple. Okay? Do that first. What we're going to do is we're going to go and zero these guys. These are global variables that are zeroed, static variables that are static local variables that are zeroed. And then we have other ones that are not zeroed. They're given specific values. They're initialized right when the program starts, before a single line of main has been run. Heap is where we dynamically take pieces out and we allocate memory. We pull some memory, say, hey, I'm going to use you now. And then I'm going to make sure that a pointer to that memory is good. And then I'm going to put stuff there. It's like having a guy direct you to your stash in Rust. I'm going to say, hey, I'm going to hide a stash over here. You, guy, remember where this is. It's like, I guess the guy is the map. We have a map, and on it I mark where my stashes are. And I look and I go and use the stashes. Stashes are on the map. I have to take pieces of the map at a time. I can't just use the whole map. I have to say, hey, I'm going to use this piece of the map, okay? Map, remember where. Map tells me where the piece of memory is. Oh, I gotta go to the bathroom. 10 minutes? Be quick. See how fast I can be. Be right back. How fast? It's not bad. 3-minute poop. Okay. Hurt. Okay. Took longer. Heap, we dynamically allocate variables from. Okay. Then the call stack, which is a place in the stack where we keep track of where we are. Also, I guess, right? Or function. Oh, hold. Or function parameters. Does drawing help me remember things? Maybe. Feels like it might be helpful here, so I'll do it. So it seems like we have this big guy called the stack. Stack. And we have a section here for the code, but it's really in binary. 0101, right? We also have a space for global and static variables that are value initialized, another set that are not value initialized. We have the call stack, where we have parameters and temporary. Well, I mean, it's not really temporary, so I guess I'll just say local, the ones that are going to be deleted once the function returns. Local variables. What else have we got here? What have we got? The heap. Oh, the heap is outside. Heap. And this guy is stack. We can dynamically say, hey, I'm going to use this piece. I'm going to say right here. I guess we could have a local, really. Local is going to reserve this little piece of memory and point to him. And I could put values there and I could use it. It's a local. It could also be global. What else? Code, heap, call stack. That's it. Okay. Heap and stack. It's cool that it's cool that we know now that, hey, global variables, static variables that are created at compile time are, I guess it's true that they're static, not just static local, also static member variables. Static global is the same shit as just being global. It's going to be zero initialized, and then it's immediately going to be initialized. Since make a global also static. Can you even? I'm going to do global static x. Oh, and it's an int. Static. Can. I don't know why you want to make it static. Static means that it only exists in this file. It has internal linkage. Make it extern. And then, which would void the purpose of making it static. And then it would be zero initialized immediately on the program start. Because it's global, it's also going to be actually initialized with whatever value. So if I put in 5 here, it's going to be first initialized with 0, and then it's immediately going to be overwritten 5. Maybe the other ones get 0 initialized first, then that might make sense. What else have we got? I need to stop with saying too much. It's been when I'm trying to get to this thing, but it's silent. Okay. Restore. The heap segment, huh? Is that a piece that's in the stack? Oh, my water. Go back. I gotta wash this cup out. Lemonade, I'm excited. It's been a while. Months. Holy shit. Okay, let's go. What am I hearing? Crackling. Fan on? Good. Cold. It's hot. A lot of fans in the other room. Yeah, kind of hot. The heap segment keeps track of memory used for dynamic memory. Oh, that makes sense. So I guess we just call it a segment. The segments are pieces of the entire bit of memory that we have. Or at least the pieces that are, maybe a program can't use all of the heap of the computer. So maybe a program is given like a reasonable amount, but how much is reasonable? Maybe that's where you have to actually allocate. So like maybe Minecraft has a small stack, but the heap is actually how much you're allocating to Minecraft, which you can do from, I think, 1 or 2 gigs up to whatever. So you give it 16 gigs. Well, it's not going to just be using the 16. I think it'll be using the 16 as it needs it. So is the 16 is the entire 16 a heap segment? Sounds like it. So in the stack would be any extra, the overage, so like 16, whatever the hell. Okay. So a lot of memory, 16 gigabytes? Holy shit. Isn't Tera's 12. Is it mega? Is it mega giga? It's got to be, yeah, it's 1,000 times 10 to the 9, so it has 10, giga has to be 10 to the 12. Shit, a lot of bytes. That's it, they're only bytes though, so they're tiny. Okay. So the heap segment is the memory that a program can use, and is memory that is used for that is dynamically used. Memory used for dynamic memory allocation. Heap segment keeps track of memory that is used for dynamic. So we say I use heap memory via dynamic memory allocation. So dynamically allocating it, bringing it into full use. Opening it up. It's like the heap is a big floor of doors, like in Monsters Inc. And you can open them up. And if you open it up, then you can jump through and use it and get the values on the other side. But you might want to make sure that the door can be opened up, that it's valid, that it actually has value before you open it up, and then you're stuck. Undefined behavior. Talked about the heap a bit already. C++, when you use the new operator to allocate memory, allocate it in the application's heap segment. For example, we don't need anything else. We'll just say an x is new int. Excuse me. Oh, why am I initializing this? I need a pointer. Excuse me, a pointer to an int. This is a new int being created somewhere. Excuse me, and I'm getting its address. New returns the address to a piece of memory in the heap that stores this type of object. I could make, let's see. Couldn't I make this a pointer to an int pointer and then make this, hold on, how do I do this? Int pointer. Oh, hold on. I guess, oh, this is how I have to do it. I have to say an int pointer like this. So x is a pointer to a pointer to an int pointer. So we can get a new int pointer. Right, and we can initialize it with null pointer. Boom. And I could check x to see if where x is pointing there is a thing there. We set this to be null pointer. And a cuticle. Okay, cool. So we can do this. We can declare that there's a new piece of memory in the heap that we're using dynamically allocated. Assuming an int is 4 bytes, we have a pointer to an int, and we're giving it this new int, but it isn't initialized there. I don't remember if it's 0 or if I think it's uninitialized. I think that's unsafe. Oh, and if we do an array, then we do it a different way. We still do a pointer to an int. We'll call it x. And we want a new piece of memory. What is the memory? It is for an array of integers. How many integers? We need the size. We could say int size. And we'll say it is 3. This is how you get dynamic runtime size besides standard vector, runtime size arrays. We can initialize them to make them empty. Or hold. Oh, okay, you actually do need. Okay, so size t is fine. Then we could also say that, give it the values, then do something with x. Cool. And said I wasn't gonna pick the nose, but I'm stuck. Stuck. Hard to breathe without. I don't know if it's eventually just gonna fix or what. It's in your nose is just genetically shut. How it is. All right. Pointer. You don't have to worry about the mechanics by how the allocation actually happened. Fuck. Actually. Oh, no, it's connotation. Good. Okay. But how free memory is located, meaning we're looking through this sea of potentially open memory, picking a piece. I mean, it seems like, in this case, it at least has to find a place that has room for 40 bytes, right? 10 integers. Search probably is determined by the size at least. Oh, I didn't know what this guy was saying just for a second. It makes sense. If you do it once, you do it again. That does not mean that those two guys are sequential. Absolutely not. Let's do it. Let's try. I want music. Oh, James McCann again. These guys are great. No, not playlist. What beautiful playlist? That's the strat. What's happening here? Nothing. Good. No, not this. Why do I keep? Oh, it's because I subscribed. I didn't actually add any music to my. I need to get muscle memory going. I need to go and click the name. Okay. Oh yeah. Let's check to see if these guys are sequential. All right. Okay, yeah, definitely not next to each other at all. All right, because it's 0 through F. So 7, 8, 9, 10, which is A, B, C, right? So we're at least 5. We're 5 away in this dimension. and 8 away in this dimension. Yeah, okay, we're far away. We're not, like, we're in the same area, but we're pretty far, I think. Yeah, it's like here, and then here versus, yeah. Not sequential addresses, yep. When it's deleted, the memory is returned to the heap and can be reassigned to future allocation or receipt. Makes sense because free it, hey, it's available, it has garbage value now, which is why when we want to reallocate it later, we want to initialize it. I don't want to use whatever shitty values it has. Let's do role play. Good. Okay. Boom. Ow. Yep. Oh, really? How did I touch that? Comparatively slow, meaning that, what, it's maybe not super optimal? Or do we mean, how do we mean? Yep. Yep. But if you have cleanup, then number 2 isn't bad. And do we mean slow, meaning we have to actually do it? It's not automatic? How do we mean? This is also fine if we're doing it. Oh, oh yeah, because apparently there's the object that's in memory. Like the best example is apparently this. Apparently it is when we're receiving something by reference, const int reference, or we'll make something that makes more sense. Constant string reference, string, and we'll print it. Yeah. I should have done that better. Delete, there it is. So we're printing a standard string in this case. We're passing it by reference, so we're looking at the actual place in memory to where name is and printing that value. So there's no copy being copied here and then used. It's instead looked at via reference. It's received via reference. I don't like passing via reference, but sure, we're passing it and looking at it, so we're passing it via reference. Okay, we're passing it and it doesn't matter. Okay, so point here is in this case, if we had just actually a better case is int print. Oh, sure, we'll just do print. Or we could do I need an end bracket. Okay, so we could do this with an in, we could do this with whatever. Okay, I can print this and then hold. All right. So what's happening? We're creating a name and then we're printing it. And name is being copied character by character to create another standard string, and then we are printing it. The problem with that is it takes a lot of effort, it takes time and processing power, compute, I guess. Excuse me, to copy a standard string because there's a lot going on, I guess. Or at least the way of copying it is expensive. Compared to copying an int, we take 1 and we have this temporary variable, temporary object 1, and it is copied to another int here. That copy is cheap. The point is this. Once the data is here, after the copy, when it is in a parameter, and we have the value here, it is in a CPU, a processor register. The value is somehow stored in a place where the processor can just execute it. Boom, it has the value. But if we instead do this, we just add we add this, let's make it const, because now we can use an R value, which is 1. If we make it const, then, if we do it via reference, then what happens is we're instead looking at where name is in memory and looking at where 1 is in memory. We aren't, I can't tell if I just got a tonsil sewn out or if it was some phlegm. What the hell happened? Okay. So when we're looking at it in memory, we have 2 things to do. We can't just straight print it. We have to first, when we try and print it, we have to go use thing. Thing is basically a pointer to this type, a pointer to a standard string, a pointer to an integer, a constant standard string in this case. What we have to do is we have to use that pointer to then go there in memory, and then we have to print the value. So there are 2 things that need doing. So it's actually more intensive to use something via its reference than it is to just print the thing itself, because we have to use the reference to get the value we're looking to print, and then we have to do so we have to find it, then do it. It's the same as having a piece of paper be in a book, and I have it's the same as a piece of paper being on a desk, and I pick it up and I read the word, versus a piece of paper being in a book, and I have a bookworm, what do you call it, a bookmark in there, and all I do is flip to the page real quick, and it's there, and I can read it. But the point is, I have to flip to the page first, and then use it, versus just picking the page up. The helpful part is that instead of having to copy the entire page over, even though it's already on the desk, it's already here, I have to copy it and then use it. It makes more sense for me to just look at the page and use it, which means we have to do it this way, which means we have to do 2 steps instead of 1 to avoid copying, which is why it actually makes sense to not do reference if we're doing this guy where we're only copying an integer, which is cheap, because then we only have to do 1 thing. All we have to do is use it after copying it. We don't have to go and find it. My nose is whack today. Okay. On and off. G. Of course, it's miles away. Love the arpeggio. This is nice. Okay. Okay, it's slow, must be accessed through a pointer. Dereferencing a pointer is slower than accessing directly. Exactly, we just said it. Oh, here it is. So this is basically what references are. This is what references are. Not basically, this is what they are. They're just dereferenced versions of pointers. Excuse me. That can't be reseeded, so they can be safer. Hold on. It feels like stuff is stuck. Like right here. It's just a collection of mucus. All the hairs in my nose are bent towards each other, and I need to open them up so I can breathe properly. Okay. So it's the same as this. If I pass, well, can't do this. I need a pointer because I can't receive an R value via a pointer. So we'll just do int x. And then I'm going to pass the address of x. And we're doing a t pointer, a pointer to a t. So in this case, it's a pointer to an integer. And really, I mean, I don't need this. Oops. Okay. So we have a pointer to an integer, and we are dereferencing it. And really what we need to do is if thing then use it. So 0 in this case, or 5. Ow. Simple. Okay, and really it should be const, so we can't modify it, but it's fine. Because we're just printing. But the point is, we have an address, and we have to, one, evaluate this guy to go and find 5, and then I have to print it. Can't just print it. The weight is in this. I have to do this part first. I can't just print. I have to start printing and go get him first. Dereferencing a pointer is slower than accessing a variable directly. Because the heap is a big pool of memory, large arrays, structures, or classes can be allocated. Makes sense. That's where we want to make it. I don't know how large is, but alright. Call stack. Stack. Keeps track of all the functions that are active functions. So the ones that are, okay. Active functions meaning ones that are actually in the call stack right now. The call stack at minimum is main. When the program runs, main is run. And I don't really need a tracker to know whether one function is ended or not, but we do need to know where we are with multiple functions calling. That's how we're able to get back to reality from recursion. Oh, that's why my nose is messed up. Days ago, I had I forgot to take an allergy pill in the morning. I try and not do a bunch of medication. I take a little vitamin D, and then I take an allergy pill. I took one this morning. I forgot to take one day. I guess I chose not to take one for maybe 2 days actually. And then my nose was dripping all fucking day. And I went to sleep with like a half-breathing nose. Missed it, isn't that? And now it's all just dripped in. It's all there. Oh, this guy. He always takes his fucking foot out, bro. But he jams it. This guy is great. Bum, bum, ba-da-da. Bum, bum, ba-da-da. Bum, bum, ba-da-da. I've never heard Snake's theme, really. Okay. Keeps track of all the active functions, call but not yet terminated, start of the program to the current point of execution. Let's see if non-dark mode works. Oh my god. And no thanks. Oh, that's why reading has always been weird. I have everything on dark mode. It's harder to read when it's not black. Just because that's how text is. Apparently it blends together more. Track of all the functions. So it keeps track of our function call stack. I mean, that's what it is. It keeps track of the list of functions that have yet to return. Start of the program to the current point of execution. And time's flying. And handles the allocation of function parameters to local variables. No. Uh, oh, I didn't that. That was gonna be higher. Current point of execution that handles allocation, all function parameters and local variables. So it handles all the function shit. Okay. A stack data structure, meaning that we pop the function that has yet to return, I guess, onto the stack, maybe, and maybe pop its objects into it, or maybe the function holds them. I'm not super sure. I'm not sure how the stack handles the allocation. Please. Okay. Data structure is a programming mechanism for organizing data. Okay, cool. Since some arrays and structures, yeah, that makes sense. It seems like they're likely complex types. In these cases, it's a synthesis of multiple types or multiple objects, but is created of the fundamental types. Structs and arrays. I mean, classes too, I guess. Um, Not enum. Well, it's a complex type, but I'd say an enum could be. For example, we have yeah. Well, sure. Really, you have an array of all the enums, and that's how you store all the people in your class. Your 30 people have 0 through 29 in the array. I guess you could say the enum is what's actually organizing it, so we can evaluate them as is. I don't think it's really data structure, because it doesn't help with anything efficiency. I think it could be, but it's not a great example. But the override mechanism for storing data and accessing it in an efficient way. I mean, okay, enums are, yes, because we could do a for each loop, or we could do well, not a for each, but a loop, and loop through from the first guy in the class to the maximum piece of the class, which would be one past the last guy, and it would loop through all the guys. What we could do for first student initialized to be for current student initialized to be current first student, last student, or until last student max, and it helps. So we can go through each, instead of having magic numbers, right through each student or student. There are many structures that are commonly standard library with stack. Stack is actually one, not because we use a standard vector to use it as a stack. Look at the top, something on the top, and pop it off. Okay, so yep, plates are the example. Stack of plates, I can. Well, I mean, but take something off the top, go on the top, and then look at the top. Oh, meaning it doesn't have random access? Yeah, because you can't choose random. Is the next. How do we do standard vector? Standard vector. I just happened to the top, but I didn't have to. I was basically forgoing. I was forgoing random access standard vector to use it to push back and pop back. Oh, I guess an input buffer is pretty similar, huh? Standard character input. Peak reminded me of it because it has a standard character input dot peak as a peak member function. We look at the top to see what the next character is, and maybe we can look next. But I mean, we usually don't. We usually just look at the top, and then whenever we extract something to the input buffer. And we pop something off, we pull something out of the input buffer. And so extraction puts something on the input buffer that uses input, but then pulls it off the input buffer. So it gets it from, it's the medium by which the user can use his fingers to put information in the input buffer, and then the computer will automatically pull it out, or at least try to pull it out. We can also look at the top and see what's going on in the computer. Does character input have a push and pop? Maybe, I don't know. Aren't they standard vectors? Not sure. Excuse me, sorry. Excuse me. Oh. Oh. Well, we know character input.peak is. Okay. Look at the top, take the top off, put a new item on. Oh, last on LIFO. Last in, first out. Last on, first off. I guess that's LOFO. But okay. Last in, first out. I'd rather say last on, first off. LOFO. This first in, first out doesn't really make sense. I mean, you can imagine a shitty fast food store where you get on, you instantly go out. First one off, you have to get off before anybody else. People inside are just screwed. Because as long as someone comes on before someone comes off, the first guy is stuck forever. Holy shit, man. Crazy good. No, no. Oh, it was her making the sound. I'm like, oh, they. This guy in the back looks like he's on. He's going speed mode. What is he doing? Like shaking that thing. Okay. I'm trying to focus, yo. I also have to keep the social connects going. There we go. That's the first stuff. As items are pushed in the stack, grows larger until we finally go all the way down. Yep. And similar to the fast food analogy, if the second to last guy never leaves, the first guy can't ever get off. Similarly, if do thing never returns, well, main can never return. Stack is empty. Push 1. Stack is 1. Push 2. Stack is 1, 2. Push 3. 1, 2, 3. Pop. 1, 2. Pop. 1. Pop. None. Better analogy? Oh, this motherfucker's doing this stupid ass mailbox analogy again, bro. Oh, and the point here is we have capacity. Well, no, that's just a raise in general. Oh, I guess it is like a standard vector there where we have a set capacity and set it. So we somehow have a marker to let us know which one's the top. We can save an index. Save the index of the top one. Whenever we pop, we decrease the index. That's the top one now. So, oh shit, Pirates of the Caribbean? Oh, he's got shoes on this time. Oh, he's maximum locked in. Let's go. Yep. Makes sense. We have 10 boxes. Our stack size is 10. That's the most we can have for whatever reason. We got 10. And then say, okay, first guy, we push something onto the stack. Okay, size is now 1. Capacity is 10, size is 1. Push another. Now its size is 2, capacity is 10. Pop. We go down. So we set the top in. We set the storage to look at where the top guy is. Oh, we added the first guy. Or added the first guy. Look at him. Added the next guy. Look at him. Add the next guy. Look at him. Look at him. Pop. Push. Pop. Push. Pop. Push. Pop. 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 Push. Push. Pop. Push. Pop. Pop. Push. 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 Pop. Push. Pop. Push. Pop. Push. Pop. 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 Use a marker to keep track of where the mailbox is, and this is our marker. A post-it note. Close mailbox. We push something on. We look up. When we pop it off, we look down. Boom, 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 boom. Call stack segment. Call stack segment holds the memory used for the call stack. What do they call them? Ensemble. Main is pushed onto the call stack. Where the call stack starts from? Who starts the call stack? I'm not sure. Operating system, I guess. Program begins executing when main is pushed and hasn't returned yet. I guess you could almost see it like a stack if you're in a game lobby looking at where your buddy is in a minigame. Oh, he's not playing a minigame. Oh, now he's in the lobby of the minigame. Oh, now he's playing the minigame. Now he's at the final 5 of the minigame. And then, oh, now he's still playing, but he's won. Oh, now he's back in the lobby. Now he's done. Or it's just a binary call stack where it's added and subtracted, done. So, playing the game. Oh, you're not playing the game anymore. Playing, still playing, not. Main is call. Main is added call stack. Okay. We show the call stack. Current function ends. Function popped off the call stack. Unwinding the stack. After this final bit of study, I'm going to do a self-test. Haven't done one in a while. It's been like a week or 2 weeks maybe more, which is fine. I don't think self-testing super often was. Well, it was great in the beginning for the main foundation, but now that it's just kind of stuck in the brain for probably a long time, at least maybe a year or 2. If I had never even looked at it again, I'm just gonna remember when you can assert, when to static assert, how allocation or how initialization works, what's the difference, all these other kind of things. Loops, some dynamic memory allocation, pointers, references, conversion, static casting, all this shit. I just got to self-test again. Now it's more like upkeep and bringing up the new stuff. Foundation's already in there. I just need to keep exposing myself to new stuff because I don't have a full foundation. It's mostly there, but some wonky planks, I think, or at least some planks just haven't been put in yet, which is why they're pitfalls. I could fall into them because I just don't know how to do it yet. Just don't have the material. Okay. When the function ends, the function is popped off the call stack, unwinding the stack. Thus, by looking at functions, currently on the call stack, we can see all the functions that were called to get to the current point. Excuse me. Meaning that if we look at it and they eventually all pop off, then we can see all the ones that were called to get there in reverse. Yep. Items are stack frames. Called so we push one, so we assign all the data for one function call into it. Marker registered in the CPU, known as a stack pointer. Track of where the call is. So I guess it is pretty similar, huh? It's like, here's the info about this function, and then about this function, about this function, about this function. Instead of it being an array or a grouping of integers or a grouping of something else, it's a group of function information. What the function is, and the stuff that's inside it. This is scary. Who's doing this? Can't tell. Tim. When we pop an item off, we have to move the stack pointer down. We don't have to clean up or zero the memory. Because the pointer is set there and we can't go further. We can only go where it's at, where the pointer's pointing. Oh, because once we pop it off and we push something back on, it will set information back there. Okay, interesting. Get a function call. A stack frame is constructed and pushed onto the stack. For our first call, frame has the address of the instruction beyond the function. Talking about the address of the instruction that is one after the function. So that when the function finishes, it tells us where to go to, probably via a go to. But somehow brings the information too. So maybe some sort of special go to. Stack frame has all function arguments. The arguments are passed into. We have the info of those parameters now. They're received as parameters. We have places of memory that are being used for local variables. Saved copies of any registers modified by the function. I don't know. CPU jumps to the function starting point. Execute instructions. So the registers are like the active pieces of memory that can be used in the function to do shit. maybe? Or at least where the arguments are. So the registers are freed back up, stored somehow. Stack frame is popped off, frees the memory. So we free the memory for anything. Return value is handled. Go back. Gotcha. We go next to the return address. Return values can be handled in different ways. It makes sense for it to be the CPU register because if the function uses it and then we clear all the stuff in the function, then the CPU passes the information and then runs the thing again. Okay. Stack grows away from memory address. What are you talking about? Oh, interesting. Some things could be closer and closer. Oh, gotcha. Don't know the next thing. Gotcha. So it's not, it wouldn't be helpful. Maybe it might not be helpful to check whether the next thing has a bigger address or a later. For example, we have main, and I'm guessing we're going to call a function that, no? Okay. So we're literally calling foo, pushed onto the stack. We then assign everything to foo. We put information, the stack frame onto the stack. We do whatever the function does, and then we return, pop it off. So. Function, we initialize, get everything set up, and then we return, go back to main, and then we're at main. Stack overflow, when we have limited size in the stack and we run out of memory, because the stack only has so much. The stack has that, whatever, 1 meg rather. Wow, default is 1. Variables on the stack, a nested function calls recall something but doesn't free. Oh, because the information of the function calls is stored as a stack frame, which uses up memory, even though we're not saying, oh, store this function as memory. Done, buddy. Probably because we keep on storing a pointer to the function, on storing return addresses and all this shit, so every time we call, I mean, just there, in int64, a pointer to an address is an int64 long int. Long. It's 8 bytes. Bro, what do we have? 10,000 of them about before we get to 1 million? Whatever. 12,400 or something? Less. 12,300. OS to issue an access violation to terminate the program because, hey, your function is accessed, or your program has accessed memory outside of the little bit that it's been allocated, or the stack. Oh yeah, or you just make a C-style array that's too big, instead of making it use the heap. Oh yeah, but ours we get an access violation because it is VS Studio. Pop. Access violation. Oh no, we should do get Stack Overflow. Nice. Okay. Huge bit of memory. Stack is not large enough. Gotcha, because it's not even big enough, so it would go somewhere else to find one because arrays are contiguous. Which means it goes outside of bounds and boom. Is that what we get? 107, blah, blah, blah. I don't even get that. Or. Oh, hold. There it is. Oh, wait. Code 0, but big F7. Code -1. I didn't get that. I is never printed because the stack wasn't even initialized, wasn't even created. Which means the program doesn't continue. It stopped before. Okay, let's see. We have a loop or something? All right. So, oh, do we have an infinite loop maybe? Hold. So, call each stack. Each stack. We have a global variable called a global counter, and we're going to print incremented global counter. And then we're going to say if global counter is greater than 0, oh, there it is, recursion. We're going to call each stack again, which means it's going to continually grow, getting more and more and more until it eventually goes. And it will go forever until technically it exceeds the size of an int, which is like whatever, 16 billion or 4 billion maybe. And then long is bigger or old, maybe something. Hold on, because an int64 is the quin, right? So we divide that. Oh, yeah. I think it's billion. Tail call optimization. Oh, and we need to do that because otherwise, tail call. Oh, and you can see how when you should run out, right? What? Oh, how far did we get? Oh, wow. 3.9 kilobytes. That's it. Holy shit. Stack Overflow is early. Oh, no, but that's the counter of integers. Oh, wait, hold on. Or no, that's the amount of calls. We got 3,800 function calls. 3,800 times, say 10, it's 30,800 bytes, which is 10, 30 kilobytes. Math doesn't add up, but there's probably a bunch of other overhead things that I'm missing. The stack frame is pushed onto the stack every time each stack is called. It calls itself. Eventually, we'll run out of memory. Okay. There it is. Shit. Call that. And mine was 1,000 something, 1,800. Version. Allocating memory on the stack is fast. Meaning we just do it automatically instead of having to read extra stuff. It just exists right there. CPU register. Boom. There we go. Memory allocated on the stack stays in the scope as long as it's on the stack. Huh. Oh, memory allocated stays in scope. Because once one has been popped, or one has been pushed on, and then it pushes another. Previous has to stay on until we finally return. So once it gets popped off, then it gets destroyed. That makes sense. Allocated. There it is. Allocated versus free. All memory on the stack, or all memory allocated on the stack is known as compile time. Oh, meaning that the the location where stack memory exists, all known. I can access those specific addresses. To fuck around with the stack and get returned to early, or think free memory I actually want to. And how does it return if it already got freed? I don't know. So the stack is relatively small. Like if a function freed the memory of the function, called it. Small, don't do stuff that does a lot. Okay. Recursion. Function that calls itself. Here it comes. Countdown. 5. Okay. Create 5. Call. And then we say pushing. Oh, push number 5 and line. And then count down with 5 minus 1, 4. Countdown is called again, and it receives 4. Push 4 with 3, receives 3 with 2, receives 2, 1. Count 1. Oh, because it's going to go forever. Hello? That'll do it, buddy. I was wondering what was wrong for a second. Oh, we're continuing forever. No if statement to check when count hits something. And there's no for loop, nothing. There's no, I guess it wouldn't even have a loop because one would call it over and over and over again. It's not calling it once, calling it again, calling it again from a loop. It's calling itself each time. 5 is called, push 5 is pretend, countdown 4 is called, 2. Sequence countdown with a number, calling countdown n minus 1 continues because once we do 2, we get 1, 1, 0, 0, negative 1, 1, 2, etc. Continue. But then we're going to eventually stop it like that. We're going to get a Stack Overflow. GG. GG. Function call causes data to be placed on the stack. Yeah, because we have these stack frames that have pointing to the function or has tracks where the memory is allocated, has a bunch of shit. Stack pointer. When it never returns. We'll just keep calling itself forever. It's never returning because there's no end condition. Oh yeah, here it comes. Run out of memory, we get Stack Overflow. Oh, in this case, it counted to negative 1,730. How far do we get? Good, doesn't even run. GG. Oh, that's cool. Oh, is that this tail optimization? Never mind. Tail call. Oh, here it comes. A tail call is a function call that occurs at the end of a function. Functions with recursive tail calls to a non-recursive function. How does it optimize it? Does it go and find out how many times it's going to call itself depending on the value it gets? What if it's not known to compile time? recursive termination conditions. They work like normal calls. Termination condition, base condition. Meaning the thing that yields a control path that doesn't call itself. Recursive termination. Okay, so for example, what if we want to do it 10 times? Okay. If we call print high, we could have a thing. We could say we print high, then we say if I guess it needs an end. Okay. Say if x is less than 10, then print high, then decrement x and print high x. Oh, hold. Oh wait, hold on. Here it is. Less than or equal to, or rather, we could say, oh, duh, if x is greater than 0. Or we could say greater than 1. And so we print high, we print 10 high, x is greater than 1, so we decrement x, print it. The point is eventually we get to 0. When we're at 0, do nothing. Okay, so we're doing count to 5. So we're saying if the count is greater than 1. True, I guess we don't have to do that, huh? Smarter. Okay. We start with 10. Print 10 high. Then x is 10. 10 is greater than 1. So I'm going to call it 9. 8. 6 off with 1. 0. 0 is not greater than 1. Or rather, 1. 1 is not greater than 1. So we're not going to do it again. So we start with 10. We go down and we print decrement 1. Print high, 1 high. Then we check and then we end. Okay. Start a recursion. The net is close. this real quick and then work on the game a little.